this conference. So the pleasure to present Sascha Troscheit, who talk about the localized measurement of complexity for self-similar attractors. So please.
Now I'm switched on. Well, first let me start by thanking the organizers for inviting me to this talk, and especially Marcelo Viana, who's not here today, for enabling me to stay at IMPA for the last month or so. So this talk is, well, a rather light talk on Euclidean geometry, and just Euclidean geometry. I'm not considering any other metric. But as the workshop's entitled Combinatorics, Number Theory, and Dynamical Systems, I thought I'd put in at least some weak links to the other two. Dynamical systems is obvious enough. Attractors, you iterate some functions, okay, fair enough. But combinatorics, number theory, well, they're a bit of both. I promise you I will mention Dirichlet's approximation theorem at least once. And combinatorics, there will be some things about arranging words, which it's a long shot, but it's combinatorics. Right, so let me start by setting the scene. So I'm mostly interested in things commonly known as fractals. So at least they are attractors of a collection of maps called iterated function system. You can define it on many different spaces. So compact, complete macrospaces are usually the thing. Finite collection of maps, you iterate them through and you get something which is a unique set. So Hutchinson back in the 80s proved this rather important theorem that, well, at least he gets quoted in all the other papers now, that there exists this unique, compact, non-empty set as long as there are a finite number of contractions, and there are contractions, strict contractions. And we call the unique set E that satisfies this the attractor of the iterated function system, which I denote by double stroke I. Now, having this definition, you want an example, of course. I could give you the regular examples like a Cantor middle third set. So you take one maps contracts by a third with fixed point 0, the other one contracts by a third with fixed point 1. But instead of that, I'm considering this one, the Sierpinski tetrahedron. You take 4 maps, scaling each by a half, arrange them in a nice fashion. Why am I doing this? Because there's a nice statue out there with a nice picture, which is, you can find this outside of the Newton Institute in Cambridge now. It was given by the Polish government to the Queen. The Queen did not appreciate the beauty and so gifted it to the University of Cambridge, where it's now. Right, okay, so I'm mostly interested in dimension theories. To say something meaningful about Hausdorff, packing, box dimension, about these things, you want to restrict the classes because just having iterated function system is just too big. So one of the most commonly considered ones are, for example, the self-similar sets. Well studied, lots of results since God knows when. So self-similar are just similitudes. I define them just on RD, so just contract them. There's an isometry in there so you can rotate and reflect a bit and translate it a bit. Nothing fancy. The other thing I will consider are so-called self-conformal attractors. Also nothing fancy. You just have conformal diffeomorphisms. They're also strictly contracting. They don't have to be strictly contracting on the whole domain, but let's just assume they are. So self-conformal, self-similar, both have these unique attractors as long as they're contracting. And then you want to say something about the dimension. So one of the easiest to explain dimension, I'm sure you're all familiar with it, is the box counting dimension. You take any old set, let's say it's a subset of R2. Let's also assume it's compact. And what we want to do is we want to cover it by some balls of radius. I call them epsilon there. Epsilon. So we cover this by balls, and this quantity n epsilon is just the minimum number of epsilon balls you need to cover this set. And you want to find some relation between the number of balls you need to cover this set and epsilon itself. So some relation between n epsilon and epsilon. And what you would expect is some kind of power law in there. So you have some kind of exponent minus alpha. And this exponent there would be the box dimension. Formally, you take the limit of the logs, and limits may not exist, so you take lim sup, lim inf, have an upper box dimension, lower box dimension. And if they coincide, we talk about the box dimension. Now the other one, I'm using the classical definition, not the one that we've heard earlier today, the Hausdorff dimension. So this is done by first defining the Hausdorff measure via Hausdorff pre-measure. And what you're doing is you're taking covers again, but you're not counting how many sets you need in the cover, but you want to estimate them differently. So you want to sum up not the number of them, but rather the diameter of them to some power. So in some sense, this is a more efficient way of covering things and measuring how efficient this is. And with a nice, countable, efficient cover, you can get the exponent s that you need to cover it down. And the lowest s for which there exists this measure, which is finite, is called the Hausdorff dimension. Now the last one, I suspect most of you have not heard about this, is called the Assuat dimension. Again, you take a set and something in here. What you're now doing is you're trying to cover this again, but first you pick a point. So this is the x, I think I call it x, yeah. So you pick some point x, and then you consider a ball of radius r around it. So this is now of radius capital R. And you intersect these two, and you're just interested in what's happening inside this region, inside this ball. And inside this ball, you're now trying to cover this with balls of radius little r. So let this be little r. You're trying to cover all of this. And what you're trying to find is the relationship between the capital R and the little r. So what you're doing is you're covering it, but you're covering balls in there with smaller balls. But notice this in here. So you're now resizing the quantity of the balls. What you're essentially doing is you're considering this ball as a zoomed up copy or scaled up copy of the ball and looking at how many balls of radius r over small r over capital R you need to cover this. Now you might think, where's the difference? Well, this definition, because you're trying to find this least exponent for every capital and little r, so you can zoom in and zoom out of this set wherever you want. You're looking for essentially the most complex, relatively complex part of this attractor, or just in general this set. And with common to this dimension and the box dimension is that it's also interesting if it's countable, just a countable set. Because if it's countably infinite, you can have some structure that gives you some positive dimension. Right, okay, so you have the obvious inclusions. The first one, lower box dimension, is an upper bound to the Hausdorff dimension. Just take the same cover that you needed for the box dimension. You can take this as a cover for the Hausdorff in the Hausdorff dimension, so it's an upper bound to that. Lim sup, lim inf, also clear. The Assuat dimension is an upper bound to the box dimension, the upper box dimension. If you consider the equation there, what you're doing is, well, you just take an R big enough to cover the entire set. You just consider the balls big enough, and you take the supremum, so the supremum does not matter anymore. You have the entire set, and because you're not varying the R, this just drops out as a constant, then you have the box dimension, the box counting dimension again. So this gives you an upper bound to it. All right, so Hausdorff, Assuat dimension by Lipschitz equivalent. So because they are, they're invariant on the bi-Lipschitz mappings, you can use them to find lower bounds on embedding problems. So you have some set, say, let's take this set, and you want to know, okay, it exists in R2, at least in this representation. Can we embed it into R1 by a bi-Lipschitz map? Is that possible? Well, this is only possible if, well, at least it cannot be possible if the Hausdorff dimension is bigger than 1, for obvious reasons. But it can also not be done if the Assuat dimension is bigger than 1. And the Assuat dimension, because it looks for this most complex part everywhere, it's a much better gauge of trying to determine whether it's embeddable or not. At least this is the reason why the Assuat dimension was invented in the first place. Patrice Assuat, he worked with embedding problems, and the Assuat dimension dropped out of his research. Now, it was somewhat forgotten in that, and it only was revived for fractal geometry about in the last just under 10 years, really. So 5 years, roughly, it has gained lots of traction to studying these problems. Right, so I also promise an easy example where they differ. And I think this will be the next one. No, not quite. OK, so this proposition, known in the literature now as the Mackay-Tyson lemma, the formulation is actually a newer formulation than the original one. This is just one of the ways of trying to find a lower bound. If you try to find the absolute dimension of a set, the upper bound, usually you do some covering argument, some hands-on covering to find the upper bound. For a lower bound, what you might want to try is you have some description, let's say, of this set. And all this proposition there is telling you you're allowed to zoom in. Let's say this looks roughly like this. And you can zoom in again. You have this sequence of bi-Lipschitz maps or similitudes in the original case. And if you find that whatever you're zooming into converges in Hausdorff metric to a nice set that you know, which is called the weak tangent, or in case of bi-Lipschitz maps, the very weak tangent. If this, let's say, converges in Hausdorff metric to this geniusly placed line in there, you know that this line, for a line we know the absolute dimension is 1, this must be a lower bound to the attractor. Right, I've used up the entire board in just a couple of minutes. OK, so first example. And I'll go here. So if you just consider the set 1 over n for all the natural numbers, and why not take 0 in there as well? Let's say 0 as well, it doesn't really matter. You can try and find the dimensions of this space. So the box dimension, well, not argument 12, you just try to cover this set. And what you'll find is, because you have 1 here, a half, third, quarter, and so forth, accumulating here at 0. For whatever epsilon you want to cover, you have some point here, some k, where everything to the right you have to cover by k of these balls, because they're so small, and everything to the left of this is now essentially like a line, at least with respect to the box dimension. You need to have 1 over the length of this line. And if you do the arithmetic, it works out this factor of a half. So the box dimension, box counting dimension turns out to be a half. For the Hausdorff dimension, a very, very efficient cover is just taking a ball of epsilon radius, epsilon squared, epsilon to the 3, etc. It grows small enough, and for every epsilon it's bounded, so you can define the Hausdorff pre-measure, and you get 0 for the Hausdorff dimension. Now for the absolute dimension, you can, again, just think of zooming into this set. So because the distance between those points decreases, it's 1 over k minus 1 over k plus 1. If you zoom in by a factor of k, what you get is points that are very close together. Zoom in by a bigger k, they're even closer together, etc., etc. So what you'll get, you'll converge in Hausdorff metric to the unit line, to 0, 1. So 0, 1 is a weak tangent, and because we know that the unit line has absolute dimension 1, it must be bounded below by 1, and because it lives in 1, it has to be 1. So the absolute dimension is 1 for this set. Now this, of course, motivates the search for sufficient conditions where they are equal. One of these is something where you have enough homogeneity in there, where things look roughly the same on every scale. And one measure of this would be alpha's regularity. So if you have the Hausdorff measure for the Hausdorff dimension bounded above and below for every ball that intersects it by the radius of the ball to the power of the Hausdorff dimension, if this constant c exists, then it has enough homogeneity such that the absolute dimension coincides with the Hausdorff dimension. Everything looks the same. No matter how you zoom in, no matter how relatively sized the balls are, you'll always get the same thing. Nothing too surprising, I guess. And you'll get many nice sets that now have same Hausdorff dimension as absolute dimension. Unit line, unit cubes, all these kinds of things. And because alpha's regularity is such a weirdly state definition. I can't give you any more easy examples rather than these few on there, but it's a big class of sets. Now, one has a classic theorem by Kenneth Faulkner, which says if you have self-similar or even self-conformal ones, this is called the quasi-self-similar, if you have sets that roughly look the same when you scale in, but this roughly does not even mean with overlaps. You could have these overlaps in these sets in the mappings, and these overlaps make everything hugely complicated. But even if you have overlaps, no matter where you look in, if there exist these maps in this theorem, if there exist these maps such that you just essentially scale the distances between them, and the relative properties of the metric are satisfied up to this constant of the length of this subset. If you have these, which are satisfied, for example, by self-similar or self-conformal sets, if you have this, the Hausdorff dimension is immediately the same as the upper box dimension, so Hausdorff, lower box, upper box, packing, all of them are the same. And this inspired the question by Lars Olsen a couple of years ago. Does this also hold for the Hausdorff dimension? If you have a self-similar set, it has this nice, it looks regular, but it need not be necessarily alphas regular if you have overlaps in there. But does the Hausdorff dimension still coincide with it? The answer to it is no, it does not. And on the next slide, I will give a proof by example. So we have this condition called the fixed point incommensurability condition, which dropped out of some further research I did on this. But the original example for this is by Jonathan Fraser. So if you have at least two maps that share a common fixed point, and the derivative at these fixed points, the ratio between them is not a rational number. That's the fixed point incommensurability condition. There should be a log in there, sorry, log of the derivative. If that's not a rational number, then you have that the Hausdorff dimension is bounded below by 1. So proof by example. Oh yes, and this is based on several research questions here and there with several other collaborators, and I'll just mention them as I go along. So this is, for example, with Jasmina Angelewska. Right, so the proof by example. And there we go. Now assume you have these three functions. You take the unit line and one maps it to a half, the other one to a third, so you have considerable overlap, and another one just to give it some structure, because otherwise it would just be the singleton, the attractor. You have these two maps, one mapping contracting by a third, the other, oh sorry, that's a half, and this by a third. And what you're trying to focus on are just the right-hand endpoints. That's firstly enough. Now, you look at the right-hand endpoints, and how are they characterized? Well, they are just 2 to the minus n times 3 to the minus m. That's all you're doing. Now, you can define some map zooming in. You can define whatever you want, but let's just zoom in by factor of 2, 2 to the k. And your similarity is now tk. Tk is just zooming by 2 to the k. So the set of all right-hand endpoints, this set tkx intersected with 0, 1 just becomes 2 to the k minus n, 3 to the minus m for the same k intersected with 0, 1. And now, as I promised, the Dirichlet approximation theorem now gives us that no matter what epsilon we pick, we can find a k big enough such that all points in the line from 0 to 1 are epsilon close to an approximation of this, up to 2 to the k minus n divided by 3 to the m. And because you can do this for any epsilon, you just have to pick a k big enough, what you'll get is that the sequence of sets intersected with it converge to 0, 1 in Hausdorff metric, or rather the Hausdorff distance between them is converges to 0. So the unit line again is a weak tangent and becomes a lower bound to the Hausdorff dimension. And the general case is, well, you have these fixed points and you are just trying to find some set which is very dense, not in the dense definition, but which is very complex with many other endpoints that are distributed enough with enough irregularity such that if you zoom into it at certain points, you'll get some interval, which is quite tricky in the general case when you have rotations in there. But this fixed point incommensurability condition is not the best we can do. There's something which is called the weak separation property. The original definition is due to Lau and Guy, and it is a rather inconvenient condition. What you're trying to do is, from a dynamic perspective, you look at the words that are generated by whatever is the indexing set of your iterated function system. You look at all the different coding possibilities, all the different concatenations of the maps, and for all of them such that there exists some set D such that they are all roughly of the same diameter and not the same map. You look at this set and you want this cardinality bounded above by some gamma. It's a really, really inconvenient theorem. It's similar to the open set condition if you're familiar with it. It just says there exists a set. It doesn't tell you anything about how to construct this set, and it might just be a very abstract setting. But there is, at least for self-similar IFS, a nicer way, a nicer algebraic way for it, where you consider this set capital curly E, or epsilon if you want, of the inverses according to words V and W, distinct words, and for the weak separation property, well, firstly for the open set condition, and this is also quite nice. You have now an algebraic condition whether the open set condition is satisfied or not. Just by looking at the closure, where I'm with respect to a metric on, let's say, the sup of the difference of the functions on some compact space. If in the closure of that space you don't have the identity, that's equivalent to saying the open set condition is satisfied. But you might have the identity in this set to start off with. For example, you might have two contractions, one contracting by a half, one contracting by a quarter. Now, of course, applying this map twice gives you this map exactly. And the weak separation property just says, okay, we still allow this. It's still nicely behaved. You have these exact overlaps in some sense. And what you're doing for the weak separation property is you're allowing for the identities in the original set to be thrown out and then look at the closure. For example, this set satisfies the weak separation property, but not the open set condition. And it turns out that there's a very strong link between self-similar and self-conformal and the weak separation property, inasmuch that if a set satisfies the weak separation property, then the Hausdorff and Assert dimension are the same. First one due to Fraser, Henderson, Olson, Robinson, bunch of people, then at Warwick. The case that, so if F does not satisfy the weak separation property, then the Assert dimension is bounded below by 1. The next paper, the Kenmaki and Rossi paper from June this year, I think, they beaten us to the punch on at least half of it, was that they proved that for self-conformal, if you have the weak separation property, you still have Hausdorff and Assert dimension coincide. But what Jasmina and I were able to show is that if the Assert dimension, if the weak separation property is not satisfied, then the Assert dimension is bounded below by 1. We can't do better than 1. There are examples that it's just not possible to do that. But if you consider just attractors subset of R, this gives you that it is maximal to begin with. So at least in R, it's a nice, strong result, and this nice dichotomy between the two. Okay, how am I doing for time? Okay, good. Right, so I'll do a slight break in style because I was, over the last few months now, considering a more random setting, where instead of having one IFS, you vary the iterated function system at every step of the construction. Not just that, I was doing a more generalized model where you had a graph-directed system. So for a graph-directed system, for deterministic to start off with, you start off with a graph, finite graph, directed multigraph, so you might have different edges like this, and most results want it to be strongly connected, so let's do a strongly connected one here. If you then name all the edges, A, B, C, D, and some others. The graph-directed set is for every one of these edges, you associate a map with them, and you have, what did I call it? Double print G. You have this collection of maps, F, E, E are in the edge set, and the attractors now the set that you get by this iterative process of taking any point and then you iterate it through by these maps. But the only maps that are allowed are the ones that are allowed by this graph. So think of this, say, as an automaton. These are the only routes which you're allowed to go through, and these are the only map combinations that you're allowed to go through. So if you've applied map A, you must be in this state, so you can't apply anything other than B in the next step, etc. Normally, for most results in the deterministic setting, you want this graph to be strongly connected, because if it's strongly connected, you get 3 classes of infinite words, each depending on the starting position you were in. But if it's strongly connected, the Hausdorff dimension and all the other dimensions will coincide no matter where you started off with, because there's enough of this mixing going on between those. Now, my setting is similar to that. So I've taken, instead of one graph, I'm taking a finite collection of graphs. So let's take this graph here, and let's take another graph, sharing the same vertex set. And let's do this. Now, the only conditions I stipulate on my end results are that there's a condition called stochastic strongly connected, and that at least every vertex has at least one map coming out. So we're not stuck. There's just this condition on non-extinction. Any other conditions? Well, I'm only looking at similarity maps either, and I'll give you a motivation later on. So I'm doing it the other way around. First I'll describe what it is, and then later there's some motivation for why am I doing this. Now what I'm then doing is just having another sequence just for these two maps. Let's call this one gamma 1 and this one gamma 2. And I have now a collection of graphs of gamma 1 and gamma 2. And what I'm doing is I'm starting on some vertex, let's call this V0, and I'm then picking a graph randomly according to some probability measure. This probability measure is just a very simple probability measure given just by a probability vector. So in the end, what I have is a Bernoulli probability measure on the space of all sequences, infinite sequences with 1s and 2s. And I just pick these sequences according to the probability measure, and they give me a family of, in this case, 3 attractors for each of those vertices. Now, what I wanted to know about this was in regards to self-affine sets. Affine sets are a lot more interesting because they are a lot more complicated. Now, if you just have an IFS given by affine maps, you can have not only rotations, but now you can skew it in different directions, and it just becomes immensely complicated to say anything concrete about the dimension of them. Even if they're contracting, even if they have these nice conditions, it's still very complicated. So I was looking at a class which had just the simple case that everything is still aligned and you don't have overlaps. So you map it down, you can rotate it by multiples of 90 degrees, but you're not allowed to put any skewing in there or any half of these rotations. But looking at these class only, I wanted to know some results, and I wanted to, in the end, find the box dimension of these, the almost sure box dimension for a random version of these. But I needed to know results about the projections, especially 2 projections, the horizontal and the vertical. And if you look at the horizontal and the vertical, the projections are either random iterated function systems in the normal sense, where you just pick one if there are no rotations, or you get these graph-directed systems if there are rotations. So my question was, does the box dimension exist almost surely for the projections? And this was a strangely difficult question to answer, and took me quite a while. And this is roughly one of the results of this. But in the end of studying these, I also found that the box dimension not only exists, it also coincides with the Hausdorff dimension of these random systems, almost surely. And I was able to derive the Assert dimension of these sets for some other conditions as well. So I will now, yes, I've got time, give the construction of those that I needed just to state the results, which looks at first needlessly complicated. I apologize. Right, so if you were to just look at these graphs and the codings of these graphs, you could identify each edge with a unique identifier. Simple enough. And what you then want to do is, well, we want to code all of them, but we want to have a relation between our omega, little omega, which is in the set of all 1s and 2s to the n. By the way, I've done it for finite collection, not just for 2. This is just for the example. So any randomly picked omega, and for this sequence, you want to construct the attractor. And in the end, I wanted to find a nice algebraic, or at least some hands-on way of describing all the cylinders. And the easiest way to me seemed to be, well, at first it seemed to be just a tree, a random tree, but that didn't suffice because I needed some other construction later on. So what I did instead was reappropriate some symbols with the O dot and these, and I just gave them different names. I defined essentially the free semigroup on the generators there. What I'm taking is, I'm taking all the g to the e that are just the symbols defining all the edges for all the graphs. I have two other symbols, which is the empty set symbol and epsilon 0, which is the empty word, and the nothing word, nothing there thing. And then I've taken the free monoid with relation this, and this is, you can think of this as concatenation. This is just taking all the individual words that you have and just concatenate them. So you get the free monoid on these things, all the finite sequences. Then take all the possible finite sequences and throw in another thing. You generate the free monoid with respect to this other operation, this plus operation, taking all these finite sequences and putting them together. Think of it as set union. That's the easiest way, putting it as set union. You have a coding, finite coding, and you take another finite coding, you put a plus in between. You define all the nice things that you want for them, left and right distributivity, for example. The concatenation obviously is non-commutative, but the plus is commutative because you have this set union, so it doesn't matter in which way around it is. Now with that, you can define the free semi-ring with the addition and multiplication in there, and I call this the arrangement of words. Now why this complex structure? Now for every graph here, we can define a matrix. Let's call this M, M1, M2, and all this matrix is doing, ooh, that should be a matrix, and another one here, is you're listing all the symbols that go from one state to the other state. So for example, you could have some letter A and some letter B. Nothing goes from the first state, from this vertex to the other vertex, so you denote it by this empty set symbol. Let's say there's nothing here and there's one map here. And for each of those graphs, you get these matrices. And now matrix multiplication just becomes concatenation in the right way, such that if you apply the right matrix at the right time of your iteration process, you get the right words. And you multiply all of them together up to a finite thing. And the first row will be all the allowable words separated by these pluses for the first attractor. Second row for the second attractor. Each of these are the vertices. And this would be a bit too complex a construction just for this purpose. But what I needed this structure really for was a stopping set, because I wanted in the end to have sets of roughly the same diameter. And to get them of roughly the same diameter, I defined these rather complicated edge sets. What you're doing now is you iterate the graphs through for every one of these paths and look once when they hit this size epsilon. But you're only looking at these graphs. So what you now have to do is let's say you want an epsilon approximation to them. Forget about this for now. You want an epsilon approximation for them. You run the algorithm through, and then you get, let's say, one path which is of length 5, and another one which is of length 6, and another one of a different length. The problem now becomes, if you want to multiply these stages together, they are of different length. You have to multiply them by different realizations of this matrix. So in the end, there's this other condition that you don't want them to intersect. You want an approximation which satisfies a strong separation condition. Leave that out for a second. What you now have is these matrices that you want to multiply, and you multiply them such that so you have something of length k, and you want to multiply the right thing with it. So what you do there is just matrix multiplication again. You just now take infinite matrices. And these infinite matrices, and I think they're on the next slide, are defined such. These etas are simply the matrices of the epsilon approximation. You take the right codings, put pluses in between them, such that they are of length q, going from 1 to 1, 1 to 2, etc. And this is just the eta q of, what do I call it, the relation omega and epsilon. And you want to put them together in some matrix fashion. And this matrix fashion is this matrix H, where what you're doing is you take a big matrix, an infinitely long matrix. This matrix has zeros along the diagonal, or rather they are not zeros because you have empty codings. So it's the matrix consisting of only empty codings, which is this bold 0. You have bold zeros here, and in each of these here you get some string of codings. These are the codings of these epsilon approximation graph for omega, this being the ones of length 1, of length 2, of length 3, etc. Because all of them are strict contractions, they are finite, they are bounded by something. So this length of this part here is finite. And then you have zeros in the end. The next step would be the one shifted. For sigma omega, the shift, second shift, etc., etc., etc. And then what you do is just multiply these together. Simple. Now, what I want is the correct sets. So I've also put in something that should be in there, which is just this. This is just a vector consisting of zeros. This is just giving me the first column of this multiplication. That's all it's doing. And from this first column, I now iterate them through. If I take h to the power something, k, I will have them roughly of the length epsilon to the k, plus some factor in there which drops out in all the derivation. And now from that, I want to go to some functions. And if you've seen the functions for self-similar sets and the Hausdorff dimension of self-similar sets, you get this Hutchinson sum. You get the sum of all contractions to a power s. And this frac r is doing essentially the same thing. I'm now taking all my codings and translating them into functions. And these are just taking the contraction rates to some power s under some rules. So what I end up with in the end is a big matrix with lots of functions in there depending on this parameter s. And I define a semi-norm on the first column. Just on the first column, I add all of these together. I look at what's happening there. And I take, with my semi-norm with respect to 1 over k, I take this function here. I take the limit out of it. And lo and behold, it actually converges, which was a rather difficult argument to show. It's not submultiplicative, not even quasi-submultiplicative, but I relied on some results similar to Kingsman's ergodic, subadditive ergodic theorem to actually prove that it converges. And this converges, and not just that, it is continuous in S, it is strictly decreasing in S, it has a unique 1. It is essentially a pressure, but I'm not taking the log in front, so it has a unique 1. And this unique 1, I've then in the end managed to prove that this gives you the Hausdorff dimension of the individual attractors just under some minor conditions on these. Then after several other procedures, and there are several other lemmas that I derived, you get to the setting that the box dimension coincides then also with the Hausdorff dimension. And I finally managed to do this a couple of weeks ago, and I thought it'd be on archive by now, which is why it's epsilon to the 1 over epsilon. It's going to be on there very, very soon. Now, just out of this, there was an interesting conjecture that I received a few days ago. Now, my results almost surely. And you can show that the upper box dimension will not coincide with the lower box dimension surely. There are easy examples. You just take some strings of increasing length, and there you go. But what about lower box counting dimension Hausdorff coinciding? This essentially drops out from my proof, but not quite. And upper box counting and packing dimension coinciding. So this might be a nice thing that holds, that you just take the upper box and the lower box, which you can, at least in theory, compute with this algorithm. And now it's completely independent or irrespective of overlaps. No matter how the overlaps are, they might be very complicated. But why am I telling you this? Well, I'm telling you this because of the assert dimension. Now, you have from the historic example by Kenneth Faulkner that upper box coincides with the Hausdorff dimension, well, if you have, irrespective of overlaps. We have also shown that if there are overlaps, okay, you can have the Hausdorff dimension bigger than it. Okay, fair enough. But what if you assume the equivalent notion for random systems, the uniform open set condition? Do Assert and Hausdorff still coincide? And the answer to that is not working. There we go. Is no. I've shown this with Jonathan Fraser and Junjie Miao last year. It's actually a very simple argument. Because it is a random system, you just have to really look at what is maximal. Well, you can pick just at any stage the thing that gives you the maximal Assert dimension. And you have these strings of increasing length, and then, yeah, Borel-Cantelli argument will give you that. Almost surely you'll find these strings that maximize the Assert dimension almost surely. So almost surely the Assert dimension will actually be the maximum of these. Now, while I was considering all my derivations with the epsilon approximation, it looked like, well, okay, if there are overlaps, I can't say much. If in each of those the overlaps are such that the weak separation property is not satisfied, okay, I have a lower bound of 1. But what about if I now assume the uniform open set condition or the strong separation condition? Can I say something about the Assert dimension as well? It should be maximal in some sense, but because of the graphs, it could be a bit more complicated. And yes, it's not that much complicated. It is something similar to just a joint spectral radius. You just look at what's the most complex thing, and I think that makes pretty much sense. And you'll find these strings of increasing length that give you these complex things, almost surely, and you get them as a lower bound, even if you allow overlaps. But if you restrict yourself to no overlaps, uniform strong separation condition, it will be an equality in there. And actually, I think I'm done. So thank you for your attention.
So, thank you very much. Do you have a question or comment?